Hello everyone, welcome to today's video where we will be diving into the fascinating world of electric current. Specifically, we will explore the difference between conventional current and electron flow, and how these concepts relate to the movement of charge in an electrical circuit. By the end of this video, you will have a clear understanding of these concepts and be able to distinguish between them effectively. So, let's jump right in. Electric current refers to the flow of electric charge through a conductor. In simpler terms, it is the movement of charged particles from one point to another. In our demonstration, we have set up a basic circuit consisting of a 5-volt battery connected to a 1 kΩ resistor. This setup will help us visualize and understand the flow of current. Conventional current flow. In the early days of studying electricity, scientists established a convention for the direction of current flow, known as conventional current. According to this convention, current flows from the positive terminal of a battery or power source to the negative terminal. It was initially believed that positive charges were responsible for the flow of current, hence the chosen direction of conventional current. Electron flow direction. However, through further scientific investigation, it was discovered that in most conductors, electric current is actually carried by negatively charged particles called electrons. These electrons flow from the negative terminal of the power source to the positive terminal. This means that the real direction of electron flow is opposite to that of conventional current. Why the difference in direction? The difference in direction between conventional current and electron flow arises from the historical development of the concept of electricity. When early scientists were exploring electricity, they did not have a complete understanding of the nature of electric charges. They observed that certain materials, when rubbed, exhibited a phenomenon known as static electricity. This led to the identification of positive and negative charges. Later, when scientists started investigating electric circuits, they observed that the flow of current in conductive materials followed a specific direction. At that time, they did not know about the existence of electrons. Hence, they made the assumption that current was composed of positive charges moving from the positive terminal to the negative terminal. This convention was established and became known as conventional current. However, as further experiments and research were conducted, it was discovered that electrons, which are negatively charged, were the actual carriers of electric current in most conductive materials. Electrons are more mobile and can easily move through the lattice structure of conductors. This understanding of electron flow and its direction, from the negative terminal to the positive terminal, came to light. To avoid confusion, it is important to keep in mind that conventional current and electron flow have opposite directions. Conventional current represents the flow of positive charges, which is opposite to the actual movement of electrons, and is used in circuit diagrams and most electrical conventions. Electron flow represents the actual movement of negatively charged electrons, which is from the negative terminal to the positive terminal. Charge and current relationships. To understand electric current more deeply, let's explore the relationship between charge and current. Charge, denoted by the symbol Q, is the fundamental property of matter responsible for electrical interactions. It is measured in coulombs, c. Current, denoted by the symbol I, is the rate at which charge flows through a conductor and is measured in amperes, a. The relationship between charge and current is given by the equation I is equal to dq by dt, where dq represents a small amount of charge and dt represents a small amount of time. Defining the ampere. 1 ampere is defined as 1 coulomb of charge flowing per second. In other words, if 1 coulomb of charge passes through a specific point in a circuit in 1 second, the current flowing through that point is 1 ampere. The ampere is a standard unit for measuring electric current and is widely used in electrical systems and devices. Integration of current. To determine the total charge passing through a circuit over a specific period of time, we utilize the concept of integration. Integration involves summing up small amounts of current over infinitesimally small time intervals. The resulting sum provides the total charge flowing through the circuit during that time period. Mathematically, we express this relationship as Q is equal to integral of I dt, where Q represents the total charge, I denotes the current, and the integral symbol indicates the process of integration. Relationship between coulombs and electrons. Lastly, it is important to establish a relationship between coulombs, the unit of charge, and electrons, the charged particles involved in the flow of electric current. 1 coulomb of charge is equivalent to 6.24 into 10 to the power 18 electrons. This conversion factor allows us to comprehend the immense number of electrons involved in even the smallest amounts of charge. It highlights the tiny but incredibly numerous carriers of charge within a conductor. Conclusion. To summarize, electric current is the flow of electric charge through a conductor. We have explored the difference between conventional current and electron flow, understanding that conventional current flows from the positive terminal to the negative terminal, while electrons actually flow in the opposite direction. We have also examined the relationship between charge and current, defined the ampere as the unit of current, discussed the integration of current to calculate total charge, and established the conversion factor between coulombs and electrons. These concepts are fundamental to comprehending the behavior of electric circuits. I hope this detailed explanation has clarified any confusion and provided you with a solid understanding of electric current. Thank you for watching, and I'll see you in the next video.